Why, hello there! Today we're going to be talking about thermodynamics, and specifically we'll be looking at calculations using three major equations. Those equations are delta G equals delta H minus T delta S, classic, delta G equals delta G standard plus RT times the natural log of Q, and finally, delta G standard equals negative RT times the natural log of the equilibrium constant. We'll give each of these due consideration. But first, let's talk about what delta G means qualitatively. So if delta G is negative, if it's less than 0, what does that mean for our reaction? Well, it means that the reaction is spontaneous as written. And if a reaction is spontaneous, it can theoretically be used to do work. We can use that energy change and harness it to do some sort of task for us. What if delta G, however, is positive? Well, in that case, a reaction is non-spontaneous. In fact, we have to do work on the reaction to get it to occur, either some sort of pressure volume work, or perhaps putting it into some sort of circuit to get electrical work to be done, etc. Finally, if delta G equals 0, what does that mean? Well, that means, dun, da, 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 we're at equilibrium! How exciting! So if delta G equals 0, we're at equilibrium. First, let's look at this classic equation. Delta G equals delta H minus T delta S. This is useful for multiple reasons. The three that we're going to be specifically looking at today are, first of all, it'll tell us, is a reaction spontaneous or not? Secondly, it'll tell us at what temperature does a reaction become spontaneous, or a process, such as melting or boiling, etc. And finally, we're going to use this equation to find out how much work can be done by a reaction at a given temperature, considering the enthalpy and entropy. So really, this equation here is what you'll use whenever you want to relate enthalpy, entropy, and free energy. So if a reaction has a free energy change of negative 0.00000000004 kilojoules per mole, is it spontaneous or non-spontaneous? Well, still negative, so that would mean it would be spontaneous as written. What if instead it had a delta G of positive 0.000005 kilojoules per mole? Well, in that case, it's positive, so it would be non-spontaneous as written. So what then is the magic number where a reaction goes from spontaneous to non-spontaneous, or vice versa? Well, it's where delta G equals 0. And that's specifically what we're going to utilize here to figure out the temperature where a reaction becomes spontaneous at. So what we can do is we can plug in 0 for our delta G, and we can set that equal to delta H minus T delta S. With a little rearrangement, we get this powerful equation here. So how can we use it? Well, let's explore right here with at what temperature does bromine boil. And I'm kind of excited because this gives me a chance to do a Dora the Explorer kind of thing. I'm going to assume that you got it right after the calculation, but feel free to pause while you do the calculation. Here we have the thermodynamic data that you need. 31.0 kilojoules per mole is the enthalpy change, and 92.9 joules per mole Kelvin is the entropy change. So please tell me, at what temperature does bromine boil? You did it! Using delta H equals T delta S, we can plug in our values. Here we have our enthalpy. Here we're dividing by 0.0929 kilojoules per mole Kelvin to make sure our units are in agreement with each other. And when we do that, we'll end up getting 333.7 Kelvin. Or if we were to translate that into degrees Celsius, we can subtract 273, and we get 60.5 degrees Celsius. Cool. Okay, so what's so free about free energy? What does that mean? Well, when free energy was first being looked at, it was considered as the amount of free work available, or free energy available to do work, that is. So, a few key things to point out here. For any spontaneous reaction, that is one that has a negative delta G is equal to the maximum work that can be produced from the reaction. Okay? So that's the energy output that can be theoretically harnessed to do work. So that's if it's negative. If delta G is positive, that means it's a non-spontaneous process. Well, what does the magnitude of delta G mean then? Well, it means it's the minimum amount of work that you would need to put in order to get the reaction to go. So let's take a look at this question here. Here we're given free energies of formation for these molecules, and we want to know what's the maximum amount of energy that we could get from the combustion of octane. You did it! By plugging in our products minus reactants rule, note that we're at 25 degrees Celsius and 1 atmosphere, standard conditions. By plugging in our values, so 8 times the free energy of formation of carbon dioxide, plus 9 times the free energy of formation of water in its liquid form. So these are our products, and we'll subtract from that the free energy of formation of our reactants. Well, octane is 17.3 kilojoules per mole, and oxygen, being in its standard state, O2 is a gas, is just going to be 0. Plugging those in, we'll end up getting negative 5,307.3 kilojoules per mole of octane. Yowzas! That's a lot of energy. Well, what about a temperature other than 298 K? Because standard conditions only mean 298 K. And, more often than not, that's not the temperature that we're working with. In those cases, you're going to use our classic equation, delta G equals delta H minus T delta S. So let's take a look here. Given these thermodynamic data, let's try to find out what the amount of work that glucose combustion can do at body temperature, 37 degrees Celsius. So we'll do this one in phases. First of all, what is the enthalpy change of this reaction? Remember, whenever you're looking for standards, you can use products minus reactants. So let's do just that. Wait a minute, but we're not given enthalpy information for O2 gas. Whatever shall we do? Wait a minute, we know what the enthalpy of formation of it is. Why? Because it's oxygen gas. It's in its standard state. 0. So take a moment and calculate the enthalpy change for this entire reaction. That's right. It's negative 2,548 kilojoules per mole. Well, let's find the entropy change then, given these absolute entropy values here. You nailed it! 976 joules per mole Kelvin. Great! Well, now how can we combine these together? Well, it turns out that enthalpy and entropy don't vary appreciably with temperature. Delta G, however, varies wildly. Temperature is one of the variables inside of our equation. Now, all we have to do is take these values and plug them in to that equation. Delta G equals delta H minus T delta S. Give it a whirl. See what you get. If you got negative 2,851 kilojoules per mole, you are spot on. So the negative sign just means it's spontaneous, and it means that theoretically, if you were to have a 100% efficient process, good luck with that, this is the amount of energy that you could harness from the reaction. What if we wanted to do the reverse reaction, however? So the reverse reaction would be taking carbon dioxide and water and mixing them to form sugar and oxygen, also known as photosynthesis. Well, photosynthesis takes energy from the sun to do. So how much work would the reverse take? Well, 2,851 kilojoules per mole is the energy that we would need to put in at a minimum if we were 100% efficient with our energy input. Okay, so the next equation we're going to look at deals with concentrations. So before we looked at how temperature affects delta G. Well, standard conditions means 1 atmosphere pressure. It means 298 K. It also means 1 molar of everything. But how often do you think you have perfectly 1 molar of all reactants and 1 molar of all products in a solution? Not very often. So we need an equation that can help us with that. First, let's take a qualitative look at Q versus K and see what implications that has on our delta G. If Q is less than K, that means that the product-to-reactant ratio that we have is less than the product-to-reactant ratio that we want. What can you do in that case? Well, a reaction would need to go forward and make more products. So under these conditions, there's too many reactants. Actually, not enough products, too many reactants. A reaction must proceed to the right. So delta G then, if a reaction is going spontaneously forward as written, must be negative. On the flip side, what if Q is greater than K? That means that there are too many products. The product-to-reactant ratio that we have is greater than the product-to-reactant ratio that we want. So in that case, a reaction would have to go backwards. It would have to go to the left, toward the reactants to make more of them. So delta G in that case would be positive. Finally, what if Q equals KEQ? Well, we discussed this before. There's too many neither. Hashtag equilibrium. The reaction must proceed? Well, there's no shift. Hashtag equilibrium. And finally, delta G must be 0. No hashtag here. Aha! Hashtag equilibrium. Okay? Classic. So, the question now is, we can do a qualitative analysis, but is there some sort of equation that relates delta G under non-standard concentrations? Yes. Yes, there is. Delta G equals delta G standard plus RT times the natural log of the reaction quotient Q. This allows us to use any product-to-reactant ratio that we have at a given time to assess what our delta G should be. Let's take a closer look. So here we have the dissolution of silver chloride. Silver chloride is a sparingly soluble salt. It doesn't very readily turn into Ag plus ions and Cl minus ions. In fact, here we have some data for it. 1.8 times 10 to the negative 10th is our KEQ, pretty small KEQ, and delta G standard is 55.6 kilojoules per mole. Let's take a closer look at that. So, if we're under standard conditions, 1 molar of everything, will this reaction proceed forward or backward? Look at this. This delta G standard assumes 298K and 1 molar of everything. That's a very positive value for a free energy change. So would this spontaneously go forward? Nah. It would be spontaneous in the reverse direction. Well, let's try it under some different concentrations instead. What is Q at 298K if the silver is 1 times 10 to the negative 10th molar and the chloride is the same? First, let's find Q and come up with some sort of prediction as to which way this reaction should go. Q would equal product over the reactants. Now, since this is a solid, its activity is 1. So Ag plus concentration times Cl minus concentration. If we plug in the values we get, we'll end up getting that Q is 1 times 10 to the negative 20th. So how does that Q compare to KEQ? The product-to-reactant ratio that we have is substantially less than the product-to-reactant ratio that the reaction is trying to get to. So that means Q is less than KEQ. Whenever Q is less than KEQ, that means a reaction is going to proceed toward the products to make more of them. What does that mean in terms of delta G? Well, it means delta G must be negative here. Well, let's find this out quantitatively. So, what's the value of delta G under these conditions? Utilize our reaction quotient here and our standard free energy change here to figure out what it must be. You did it! If we plug in 1 times 10 to the negative 20th, take the natural log, that's going to be a pretty negative number, times 298K, times our gas constant, 0.008314 kilojoules per mole Kelvin. Note we need these units to match up. And then we add in our standard, 55.6 kilojoules per mole. We're going to end up getting negative 58.5 kilojoules per mole. That's pretty negative. So that means that a reaction would indeed proceed spontaneously forward. So even though this is not a very favorable reaction for the products, if you have such an insignificant amount of them, a reaction can still proceed in the forward direction. Well, let's try it with yet again some different circumstances. What if we have silver being 1.34 times 10 to the negative 5th molar and chloride being the same? Once again, we'll calculate Q the same way we did before. And it turns out here Q is equal to 1.8 times 10 to the negative 10th. Okay, well, how does Q compare to K? That number's awfully familiar. Aha! It's the same thing. What do you know? Don't know why I made that equal sign spin. Q is equal to K. So what does that mean? It means we're at equilibrium. So delta G then must be 0. Okay? Classic equilibrium. What's the value of delta G under these conditions? Well, if we don't believe that, we can always try plugging in numbers. And if we do, we'll see that indeed delta G, this whole thing ends up being 55.6 kilojoules per mole. So 55.6 minus 55.6 equals 0. Okay. So we've got one final equation to explore. First, in order to do that, let's consider what we just said about equilibrium. So here's our delta G equals delta G standard plus RT times the natural log of Q. Well, we're going to do a little clever substitution here. At equilibrium, what should Q be? Well, Q would be equal to KEQ. So delta G, as we said before, would be 0. So what we're going to do is we're going to substitute these into that equation. We'll get 0 is equal to delta G standard plus RT times the natural log of KEQ. And then, voila! Delta G standard equals negative RT times the natural log of K. This is the reaction, this is the equation that we'll use anytime we want to relate delta G standard and KEQ. So, neat. Let's do an example here. Sulfur dioxide is a pollutant that comes out of cars. So catalytic converters, it turns out, converts them into this very acidic sulfur trioxide. And here's the delta G standard. I want you to tell me what the value of KEQ is. Can you do that? You sure can. Here we rearranged this equation. We plugged in all our values. Here's our enthalpy change. We're dividing by, sorry, not enthalpy change. Here's our standard free energy change. We're dividing by 0.008314 kilojoules per mole Kelvin and our temperature. And when we do that, we'll end up getting 3.45 times 10 to the 24th. Wow, that is a significant number. So products are heavily favored in that reaction. So finally, I want to talk about these diagrams here. Note the sign of delta G standard is actually related to the magnitude of KEQ, as we saw in that equation. Mathematically, the more negative your standard free energy change is, the greater your equilibrium constant is going to be, because it means the products are all the more favored. So let's look at these diagrams here. These diagrams depict reaction progress, and on the left-hand side we have pure reactants, on the right-hand side we have pure products. So if you take the delta G standard of the pure products and you subtract that of the reactants, what does that give us? Well, according to the products minus reactants rule, it gives us the standard free energy change for a reaction. And for any given reaction at any given temperature, that is a constant. So we have this. In this particular case, we can see that the free energy of the products is lower than the free energy of the reactants. Remember, chemicals like to be chill. Lower chemical potential energy is more stable. So when we look at these diagrams, we'll notice that the valley here is always more skewed toward the lower energy entity. What does this valley represent? It represents equilibrium. I like the analogy of, well, consider a ball rolling in a valley. If you have a ball here, the ball would roll naturally down, according to gravity, into this valley, and it comes to a rest at an area, a minimum of potential energy. Likewise, if we're too far to the right, well, then the ball would roll down to the left. What does this mean chemically? Well, what it means is, if we're anywhere to the left on this diagram, it means that there's too many reactants. We're skewed too far toward the reactants to be at our maximal stability. So in those cases, a reaction would roll forward to make more products until it settles at equilibrium. Instead, if we're somewhere over here, well, that means we're skewed toward, too far toward the products. So in that case, it would roll down this way and settle at equilibrium. We would make more reactants in order to get there. We'll talk a little bit more about that in just a moment. For right now, let's relate delta G standard. So here, what's the sign of delta G standard? It's negative. What's the magnitude of KEQ? It's greater than 1. And what's favored? We can see the equilibrium lies toward the products. Okay? In this case, well, here we have kind of like the flip to the opposite of what's going on here. Here, the reactants are lower in potential energy than the products. So the free energy, the standard free energy change, products minus reactants, would be a positive value here. What does that mean about KEQ? Well, we can see now the equilibrium is skewed more toward the reactant side. So it's going to be less than 1. And finally, what's favored? Well, as we already said, reactants. So one other thing, ordinarily, most of the reactions that we'll be looking at will have a standard free energy change between the products and the reactants. There are reactions out there that don't have a free energy change. For example, some isomerization reactions, where they're both on equal planes. In that case, actually the equilibrium lies right smack dab in the middle, a 50-50 mixture. So K would equal 1, and delta G standard for a reaction like that would be 0. But again, we're not going to be exploring those too much for our purposes. So, finally, the difference between delta G and delta G standard. Delta G standard is very specific. 1 atmosphere pressure, 298 K, 1 molar of anything, and it is a constant for any given reaction at any given temperature. Delta G, however, is based on a number of things. What's our temperature at? What is our concentration, our relative concentrations or pressures at? So, here, even though delta G standard is a constant, technically speaking, we could have any product-to-reactant ratio we want. I mean, within reason. So, if we're anywhere to the left in terms of our reaction progress, again, that means we have too many reactants. So what would happen in this case? The reaction would be spontaneous in the forward direction. We would need to make more products to get to equilibrium. Instead, if we're over somewhere on this side, past the equilibrium, well, that means that we have too many products, not enough reactants to be at that ideal ratio, and a reaction there is going to shift to the left, make more reactants. So what does that mean about delta G? If you're anywhere to the left of this point, that means that delta G is negative, right? Because be spontaneous in the forward direction. Spontaneous in the forward direction means negative delta G. Well, if you're anywhere to the right of equilibrium, that means that you're at a positive delta G. So it would not be spontaneous as written. In fact, the reverse reaction would be spontaneous, and you would make more reactants. And if you're at that point, that relative minima, you're at equilibrium. And at equilibrium, everything is great. You're at the ideal product-to-reactant ratio. It's not going to go forward. It's not going to go backwards. Those two relative rates are equal to each other. So delta G is simply 0 at that point. Thank you very much for your time, and I hope you have a spectacular day.